Okay, again, this one is pretty straightforward once we've identified correctly what the resultant forces are for our free body diagram. So the first thing to do is draw the free body diagram. So what do we have? Let's sketch out the structure one more time. Right, what have we got then? Let's break up this guy, this load, going between here and here. So what have we got? We have 2 kilonewtons per meter acting over 5 meters, so 2 5s is 10. That's a resultant of 10 kilonewtons. And that acts at a distance of 2.5 meters to the right of point A, halfway. Okay, we've got a potential vertical at A, vertical reaction, and we have a potential horizontal reaction at A. All right, now let's look at this load on the right hand side. Let's break it up into a load, a uniformly distributed load of 2 kilonewtons, and then a load with an increasing intensity from a value of 0 up to a value of, if that's 2, this is going to be 10 minus 2, which is 8. Okay, so we can say there is a 10 kilonewton load, which is 2 times 5 is 10, acting halfway along. Let's take that dashed line down for reference. So we've got 2 5s is 10 kilonewtons. Okay, now we then have to deal with this linearly increasing load. So what have we got? It acts over 5 meters. It has a magnitude of 8. Okay, so that's going to have, let's just jot it out here. We have 5 meters times 8 kilonewtons per meter, and remember it's a triangle, and the area of that triangle will be half of the base times the height. Okay, so that's going to give me 20 kilonewtons. So we have a 20 kilonewton point load acting 1/3 the way along. So let's just sketch it on here. That's going to be 20 kilonewtons. Okay, and let's see, it acts at a distance from the base of the triangle, a distance of 5/3, which is 1.67 meters. Okay, and then this one acts at a distance of 5, not 5, half of 5, which is 2.5 meters. Okay, don't forget our potential vertical reaction at B we will call VB. Excellent. Okay, so that's the hard work done. At this stage, it's just about evaluating our equations, our equilibrium equations. So we can jump straight in and say the sum of the forces in the x direction equals 0. Hopefully at this stage, we can recognize that HA is equal to 0. No externally applied horizontal forces. Okay, now let me see. Let's take the sum of the moments about point A in order to get VB. VB is the only unknown, and so VB is equal to 26.7 kilonewtons. And again, the positive number means it's in the direction we assumed, which is upwards. Okay, now the sum of the forces in the y direction, simply to calculate VA. So the sum of the forces in the y direction equals 0. And what do we have? So we have VA equal to 13.3 kilonewtons, and again in the direction assumed, which is upwards.